Greetings. This is Chapter 3, or Video 1.5 of AP Physics C's Unit 2, unit on Newton's laws and systems of objects. And hold on to your trousers, because in this video we are finally departing from our perfect physics world because air resistance will no longer be negligible, at least for this video. So if you're not, you'll be an expert in no time. So let's jump in. All right. So a velocity-dependent force does basically exactly what it says on the tin. It's a force whose magnitude changes with the speed that the object is moving at. So kind of like in this GIF here. Thanks to StickManPhysics, by the way. They make great animations. So this object is in free fall, meaning its weight force is accelerating it downwards. As that object's speed increases, it's going to increase the magnitude of the velocity-dependent force that's going against its motion. So as this object speeds up, that force is gradually going to cause its net force to decrease. And eventually its acceleration will decrease to 0, which will eventually result in a terminal velocity at some point. So this type of force typically happens with objects experiencing resistance moving through a fluid, like water or air. Yes, air is a fluid. And generally how this is happening is that in a fluid, even though it doesn't feel like it, you are smacking into millions and millions of these little air molecules. And as you accelerate, you're smacking into a higher volume of these molecules every second. And each of these molecules has a little bit of mass. And so the more of those that you're hitting every second means more mass that you're having to push out of the way as you move faster. And that's going to result in more resistance overall. So in this class, most velocity-dependent forces are going to be modeled by either F equals negative kV or F equals negative kV squared. And both of these, K is just some constant value. And the negative sign on both of these indicates that it is a resisting force, meaning that when we plug it into our sum of forces, it's generally going to be going against whatever is accelerating the object. So if you've ever taken a higher level biology class, or maybe you did this in one of your math classes, you've probably heard the term negative feedback loop before. And with air resistance, or any velocity-dependent force for that matter, we're going to be looking at a negative feedback loop. This usually just means that there's some observed quantity or effect in a system, and other factors are going to resist that effect in some way until eventually the loop reaches a natural balance if it's given enough time. Well, in this case, I'm going to use this GIF here as a reference again, and say we drop an object and it starts accelerating. Well, when it accelerates, then by definition, that means the object's velocity is going to increase in some way. As that object's velocity increases, it's going to cause air resistance acting on it to also increase. When that air resistance increases, it's going to lower the net force acting on the object. And when that object's net force lowers, it's going to cause the acceleration of that object to decrease. And at this point, the loop repeats over itself, but now at a slower rate of acceleration. And so now when the object's velocity increases, it's going to increase by a slightly lower amount. And that's going to cause the air resistance to increase by a slower amount. And our acceleration is gradually still going to be decreasing over time. And so the force from the air will never really outweigh gravity as the acceleration decreases, but instead we will reach a natural termination point or a natural balance of these forces. And that is called terminal velocity. You might have heard of it before. Terminal velocity is the speed at which the velocity-dependent force balance out with other forces accelerating the system, like gravity, such that the object stops accelerating entirely. And you can work out this force pretty easily because it is equilibrium. So if you start with the net forces equaling 0, well, you've got gravity and air resistance acting on the object. And when you plug those in, you've got mg minus kv for the net force. And if you set those two forces equal to each other, then we can work this out such that the terminal velocity would be mass times acceleration due to Earth's gravity divided by this constant k right here. So through this, we can find that terminal velocity itself is really only dependent on the mass of the object, the acceleration due to gravity of whatever planet you're on, and this mysterious letter k that we're going to go into more detail about now. I'd like to elaborate a little bit more on air resistance specifically, because it is the most common type of velocity-dependent force. It's worth noting that it can also be called air friction, so just know that those two terms are interchangeable here. And air resistance is most accurately modeled by the equation F equals negative kV squared. I say most accurately there because physicists tend to prefer to leave out the square when they're working through this force without numbers. The math turns out to work out a little bit less easily with kV squared, but it is still solvable. Now this letter k here is a collection of constants, for air resistance specifically, equaling 1/2 times rho times A times C sub D. And you're probably thinking, whoa, well, that just made things a lot more complicated. And Well, each of these letters all have a specific meaning. The Greek letter rho is indicated by the density of air, or really the density of any fluid that this object may pass through. In this case, the density of air would be about 1.204 kilograms per meter cubed. So for every cubic meter of air that you'd have, this object would weigh about 1.204 kilograms. Capital A is known as the cross-sectional area of the object's face that's hitting the air. So if you were to take the cylinder here and drop it with the circular face of the cylinder facing downwards towards the air, the cross-sectional area A would simply be the area of that circle, AC, given right here. If you were to drop the cylinder on its side, it would be represented by a rectangle, because if you were to look at if you were to look at a cylinder's side head on, that's the shape it would take, a rectangle. And finally, C sub D is the drag coefficient of the object's shape. And this is something that's really important in many fields of engineering, but it's not really something that you can calculate with an equation. It has to be found experimentally. And so I put here a couple of different common drag coefficients through various forums. And you'll notice that the more rounded, aerodynamic looking ones tend to have the lower drag coefficients. That's because air is more easily able to pass over those objects without being stopped dead in its tracks. That's opposed to something like a cube, where air molecules that hit the face are going to have a much harder time gliding around the object, and therefore they're going to lose more momentum. And that's momentum that's going to be taken out of your object as well. So there's one more thing with air resistance that I want to go over, and it might scare you depending on where you are in your calculus class right now, and that's the math behind feedback loops, known as differential equations. This is something that was developed alongside calculus, kind of its beginning phases. And outside of terminal velocity, pretty much any velocity-dependent force problem will require some kind of differential equation. So a differential equation at its core is an equation that relates a function f of x to its derivative, or rate of change df over dx. So for air resistance specifically, we'll find that the differential equation can take the following form here, where on the left side, dv over dt is the derivative of velocity, and on the right side, v of t is the velocity as a function of time. And the two things there are constant. Two other things here are constants, and they really don't have much of a bearing on the form of the differential equation, besides being important information for specific quantities that we'd want to find. So when you have a differential equation, your goal really is to find the function f of x, or v of t, if we're looking at the equation on the left, that allows both sides to equal each other. And you might be thinking, well, how the heck can I do that? Because, like, if I take the derivative of x squared, for instance, there's no way that I can get an x squared over here on the other side, where the derivative is. And you'd be right. Any equation that's differentiable with the power rule, for instance, is very unlikely to be the solution to a differential equation. But if you look back to your list of derivatives, you know that some of them kind of look like they'd be able to loop around on each other, namely sine, cosine, and exponential functions. They all have some way of getting back to the original function eventually. So we can take advantage of those functions to solve some of these differential equations. And as we're about to find, that's going to be the case with air resistance. Now, I do want to give you some solace if you're feeling uncomfortable with this very new idea, and that's that AP Physics C does tend to be a little bit more concerned with you setting up the differential equation, which is the physics problem, and not as much with actually solving it, which would be the math problem behind it. Now, in this video, I am going to solve the differential equation that we're going to set up later as a little bonus, just in case your mathematical mind is curious on how that's done. So with all that out of the way, I'm going to pull up a very basic example of air resistance so you can see some of this stuff worked out in real time. And at the end, if you're interested, I will solve the differential equation that we're about to set up. So let's jump in. All right, so for this example, we've got a ball of mass m drawn over here. It's dropped from rest. So as it falls through the air, this ball is going to experience a force of air resistance given by Fr equals kV opposite to its motion. So if you remember from the slides, we showed it as negative kV, and here the direction, the negative sign is given by the words here opposite to its motion. So we just need to keep that in mind when drawing our free body diagram over here. So before we jump into the math, we should acknowledge that we've got a force due to gravity acting downwards. That's going to be Fg equals mg. And then we have our resistive force, Fr, acting upwards over here. That's going to be Fr equals And again, we're going to consider the positive direction here to be the downward direction, the direction of the ball's motion. So over here, first, we're just being asked to find an expression for the terminal velocity of the ball in terms of k and m. You might remember we did this in the slides, so we're just going to do it in real time now again. So the net force equals mass times acceleration, always. And because we're at terminal velocity here, we can acknowledge that the acceleration of the ball should be about 0 meters per second squared. So if we sum up our forces here, well, we've got Fg minus, Fr in the other direction, and that's going to equal mass times 0, which is just 0. So then if we sub in, we've got an equation saying mg minus kv equals 0. And now at this point, we just need to rearrange some stuff. So we want to get v by itself. So we could express this as kv equals mg. And at this point, I guess we should also acknowledge that this is a terminal velocity that we're solving for here. So I'll make it v sub t. And then we just have to divide both sides by k, and we'll get an equation for vt, just like in the slides, that's equal to mg over k. And that is all you need to do for any sort of terminal velocity. Pretty nice. So next, we're being asked to write but not solve a differential equation that relates the velocity of the ball and time. Now here, velocity of the ball and time means we're looking for some kind of expression involving v and t. And kind of like I mentioned also, a differential equation means that there's probably going to be some kind of rate of change or derivative in this expression, like dv over dt in this case. So we're going to start out exactly like we did last time. Net force equal to mass times acceleration, except that this time the acceleration is not yet necessarily 0. So we have to keep it in there. So I'm going to skip a step here and just jump immediately to mg minus kv equals mass times acceleration. And in this case, just remember the velocity v here is changing with respect to time. So it is a function of time. And so we're almost done, believe it or not. The main thing here is that we note that this term right here, acceleration, is technically dependent on other factors in this problem. So one way that we can get around that is by expressing it in terms of velocity. And we can do that by the definition of acceleration, which is that it is the derivative, dv over dt, of velocity. And if we plug that in to this expression above, then we'll end up with basically our differential equation, which is mg minus kv equals m times dv over dt. And that would be considered a complete differential equation for this question. And again, AP a lot of the time is going to stop you at that point on any sort of differential equation related question on an FRQ. But again, if you hang out towards the end of this video, I will show you how you can solve this and get the actual expression for velocity for this equation. For now though, I'm going to jump over to these graphs here so we can get a visual for what exactly is going on with each of these three motional quantities. So we're going to start with acceleration because we have at least some kind of baseline for what it needs to end up at. So if you think at the start, this object is in free fall, it's moving. At free fall, it's going to start at some known quantity, which is 9.8 meters per second. Let's say it's right there arbitrarily. And we know it has to end at 0 eventually. So in between, what's happening is a smooth, continuous motion that's kind of getting increasing feedback each time. So the acceleration curve is going to kind of look like this here, where it just gradually tapers off to 0 eventually. And maybe you could draw it a little bit better, where it's like a bit more extreme at the beginning. I am terrible at this if you recall from the kinematics videos. But anything like that generally would be acceptable as far as AP is concerned, which again, they will have you kind of sketch graphs of these motions from time to time. Now on the velocity end, if we take a step up a notch, note that we're trying to aim for a constant velocity by the time we reach terminal velocity up here. So that's going to be kind of our guiding line here, is that really we'll get to a point where velocity will just be constant along this horizontal line right here. We know that the ball starts from rest, so it's going to start at 0, 0 down here. And so here we just want to draw a line that's going to go kind of like this, where again, it starts off like gaining a lot of speed at the start, and then eventually it just tapers off and becomes constant by the time it gets down here. And finally, for position, again, we're reaching a constant velocity eventually, but the object is going to continue moving. So we're still going to have a slope, but the object's position here is going to gradually attain a constant slope or a constant velocity. So let's say we start off curved because the object is accelerating at the start. We're eventually going to reach a point where it just stops accelerating entirely, and it just kind of continues onwards with a constant slope from then on, kind of like that. So in this case, to recap, what we really want to focus on is that the acceleration eventually reaches 0 for this guy here. For the velocity time graph, it's going to gradually reach terminal velocity. And then finally, for the position versus time graph, really the position is just going to attain a constant slope eventually. All right. And that is basically all there is to it with one of these problems. So with terminal velocity, you'll be encountering this right off the bat. But there are other parts of this class where we'll be encountering velocity-dependent forces. You'll find them with lots of different types of circuits, LC and RC circuits, and you'll also be finding them in magnetism in some cases when we get to magnetic induction. So for now, air resistance is all you'll really need to worry about, but know that this is a thing and it will come up. And it'll be good to be familiar with how to set up these differential equations for the future, especially going into E&M. So thank you for watching this video. And if you want to stick around, I will go ahead and solve for the velocity as a function of time coming up next. Peace. All right. If you're watching this part, I really hope you're familiar with integrals, U substitution, and a lot of algebra, because I'm going to be solving for the velocity through this differential equation here. So I'm going to start by actually rearranging this DiffEQ so that it's in the form that we kind of want it. To do that, I'm going to multiply both sides by dt just to get dt by itself, and I'm going to divide this term over. So if you do those couple of steps, you should find that this is an equivalent expression to the one above. It's going to be m, and I'm pulling that m out for a particular reason. And then over here, it'll be 1 over mg minus kv, all multiplied by this integrand dv right here. Okay, so in that form, we are going to integrate both sides because we're treating this as a separable differential equation, which means that we have a definite solution that we can find. We don't necessarily need to guess. Over here, I'm going to just write that we are going to be differentiating. We'll have the integral of dt equaling m, which I'm pulling out of the integral because it's not important, 1 over mg minus kv all times dv. So on the left side over here is the integral of nothing with respect to dt, and over here on the right is the integral of this big ugly mess with respect to dv. Now, when we integrate both sides, we're going to find that one side is significantly easier than the other. I guess I'll draw a little boundary here so we have it. The left side is going to turn out to just be t, and the right side we're going to have to go on a bit of a side quest for, because that is just not great in its current state. So over here, we're going to use u substitution to solve this, because we can get this into the form of 1 over u if we look hard enough. So u, in this case, I'm going to treat as mg minus kv, and du is the derivative of the equation above, and that will be negative k times dv. Now, if we are trying to get everything in terms of u, then we should isolate dv and hope that we can substitute something in for it. And sure enough, we can. dv, in this case, can equal negative 1 over k times du. So if we take that and we plug it into our expression over here, we can get it in the form of negative 1 over k times the integral of 1 over u times du, when we make all of our appropriate substitutions here that we defined above. And if we integrate that, we should find that this u subbed equation is negative 1 over k times ln, or natural log of u. Now at this point, we can go ahead and plug everything back into our original expression. So we should end up with the integrated expression being negative 1 over k times the natural log of mg minus kv. Okay. Crazy u sub side quest over. So now let's go ahead and come back here, plug everything back in. Remember, we have this m on the outside here, so we'll end up with negative m over k times natural log of mg minus kv. And at this point, our goal now is to isolate velocity v over here. And that's a whole other nasty algebraic side quest that's going to start by getting negative m over k to the other side. So I'm going to rearrange a little bit here. I'm going to say natural log of mg minus kv, flip-flopped, is equal to negative k over m times t. And at this point, to isolate the velocity v here, we have to do a little trick that gets rid of the natural log, which is to raise both sides to the power, or put e, or make both sides of the equation an exponent of e. And if we do that, the e and the natural log are going to annihilate on the left side, but we are left with e raised to the negative k over m times t on the right side. That is a-okay though. That just means that we've turned our solution into an exponential function right here, which does count as one of the ones that works as a valid solution for these sorts of problems. So now we're going to have mg minus kv equaling e negative k over t times t. And at this point, so I'm just making sure I'm not blocking anything here. We just need to isolate v. So if we subtract kv over to the other, or sorry, add kv over to the other side, and then subtract e to the negative k over m times t over to the other side, we should end up with kv equals mg minus e raised to the negative k over m times t. And at this point, we're basically done, because then we'll end up with an expression for v, which I'll go ahead and say is still a function of time in this case. And v, once we divide both sides by k, will equal mg minus e raised to the power of k over m times t, all divided by our coefficient k. And that is what our expression for the velocity of this object before it reaches terminal velocity will be. And note, in this case, you can still find the expression at which we'll be reaching terminal velocity here, because notice as this e term gets larger and larger, like as time increases, this e term will gradually approach 0 right here. I guess I have to get out of the way a little bit. There we go. And as this term reaches 0, we'll reach our original expression for terminal velocity all the way up here, which is mg over k. So everything is fine and dandy. It all works out. It was just a little ugly and required a bit of calculus to get there. So if you're watching this and you haven't learned how to solve differential equations in calculus lit, just know that you will eventually by the time you need to worry about this stuff. But if you already were sort of familiar, I hope this part helped, and I hope it scratched the mathematical part of your brain. So with that, the video is officially over. Thank you for watching this far in, and I hope you have a good one. Peace.